Okay. Well, I feel like we have a pretty good sized group, so I'll go ahead and actually get started now. So hopefully everyone can hear me. My name is Brianna Drescher, and I am the co-chair with Chris for this work group. So I'm giving her a break today and offered to facilitate today's meeting. So just to reintroduce myself, like I said, my name is Brianna Drescher. I'm a senior supervisor with the California Department of Fish and Wildlife's in-stream flow program. And I've been working with the CEF Tech team for a number of years. So I think today's meeting is really interesting. We have two really great presentations, and I'm excited for everyone to take it in and ask good questions and like have a good discussion. So today we have first Nick Murphy from the Nature Conservancy and David Drawley from U.S. Forest Service um, presenting on addressing streamflow depletion due to groundwater pumping, management recommendations, and emergent modeling approaches. And then following them, we have Christian Broderick from Stillwater Sciences presenting on his project using CEF to inform sustainable management criteria in groundwater fed streams in the Napa River subbasin. So with that, since we have two very like 2 hour long presentations, I'll go ahead and pass it over to Nick and David.
Oh, sorry. One other thing. Do you want to do the new member
Oh, remember,
introductions?
you're
Yeah.
right. I'm sorry, I missed that. Um, Bear with me. It's my first facilitation of this meeting. Do we have any new members that would like to introduce themselves? No, no pressure, but if anyone's out there, feel free to unmute and jump in.
I'm a new member.
Oh
Hi,
yeah. Well,
Dave, but I'll introduce myself, I guess, in a minute. But yeah,
anyone else today?
Hi, this is Casey Williams with InStream Flow. I'm a new ES as of July, and I'm a new member of this group. So thank you all for allowing me to attend.
Yeah, welcome, Casey.
Hi, my name is Krisha Skorko. I work with Trout Unlimited, and this is my first time attending this meeting. Thanks.
I'm Verna Jagor, Rainfall to Groundwater. Um, I've been here before, but I never introduced myself, so here I am.
Welcome. Okay. Well, with that, then I will officially hand it over to Nick. Thank
All
you.
right. Thank you so much. Let me just take a minute to share my screen here. While I'm doing so, I'll also just say that I'm a new member. My name is Nicholas Murphy. I'm the senior. Oh, you guys can see the right view now. Great. Hi, everyone. My name is Nick Murphy. I'm the senior groundwater scientist for the Nature Conservancy for the California Water Program. And my work recently has been thinking a lot about surface water groundwater interactions and environmental flows and stream flow depletion due to groundwater pumping. So I'm excited to um, meet with you all today and kind of present some of the work we've been doing. And David, you turned your camera off, but I was going to actually just quickly pass it over to you to just introduce yourself before we jump in.
hey everyone, David Drawley. I'm with U.S. Forest Service and based out of Sacramento, and have recently started getting into this world of stream flow depletion and groundwater pumping with Nick, and really looking to learn a lot from this group and kind of see what people need and are interested in, and hopefully share some of our observational information and work with everyone to make better tools.
Great, thanks. So today we're going to kind of cover a range of topics, and I'm going to start with some background on how we've come to focus on groundwater as an essential consideration for environmental flows to achieve sustainable groundwater management. And I'm going to talk about the opportunity and the needs of two statewide regulatory requirements to protect against the impacts of stream flow depletion due to groundwater pumping. The first is the implementation of the Sustainable Groundwater Management Act, and the second is the requirements for public trust resource considerations when permitting new groundwater wells at often like a county scale across the state. And these are two topics that we've been working on for a number of years, and we are excited to share some new planning resources and science tools that we've developed that we think we can help support, local governments, groundwater managers, conservation partners, to push forward and implement sustainable groundwater management that not only will protect fisheries and the health of our rivers, but also improve water supply reliability for farms and communities. And then we'll kind of pass over to David, and he'll talk about some of the ongoing efforts through the SEF program to fold in and better understand these groundwater dynamics through the lens of environmental flows. And so I think I love groundwater. I think it's some pretty exciting stuff. We got some great groundwater talks today from Christian as well later. So excited to chat and dig into this with all of you. So where I'm going to start today is part of a partnership with both Trout Unlimited and Cal Trout, known as the Salmon and Steelhead Coalition. And so this coalition has been working to use science-based approaches to make sure that rivers have the flows they need, not only to support fish and wildlife, but to do so in ways that also improve water supply reliability. And while most of our work focuses on coastal rivers, what we're talking about today is really an issue that affects the entire state. And so, why do groundwater wells matter to environmental flows? It really starts with the dramatic impacts that rivers have experienced due to land use changes. We've seen, of course, large-scale impacts due to historic logging practices, urban development, and a loss of streamside vegetation. And then diversions associated with growing human and agricultural water needs, especially in the dry months, has left less and less water in stream needed for fish and wildlife. And because coastal California has a Mediterranean climate, both people and fish struggle to have enough water during the dry season. And that dry season is only getting longer, drier, and hotter due to climate change. And so this results in the fact that many of our riverine ecosystems are being degraded and fundamentally altered, and they don't have the water they need, especially in the summer, to support these healthy ecosystem services that provide habitat for fish and other groundwater dependent ecosystems. This is particularly an issue for threatened coho, salmon, and steelhead across the state. Juveniles of these species they spend their first year in their natal streams, and this means that they need to survive through the summer, rearing in pools where they feed and grow before migrating out to sea. And so this makes them extremely vulnerable to the impacts of diversions and dry years that can dewater streams and increase stream temperatures to result in degraded ecosystem function. And so for many years, we've worked in these coastal watershed communities, for example, the Navarro River, to implement water management projects that reduce reliance on dry season diversions and store winter water to meet summer water needs. And so this not only leaves more water in stream for fish, but it also improves water supply security for landowners by helping them not be as dependent on unreliable summer water resources. But a few years ago, we kind of made this crucial discovery when we added up all of the direct diversions in the Navarro watershed and combined it with the quantity of existing flows measured. The two didn't add up to expected full natural historic flows. In fact, there was this big block of missing water, particularly in the dry season, and it became clear that that missing water was groundwater. And so, as many of you know, groundwater and surface water flows are interconnected. And in the wet season, rainfall infiltrates into the soil and recharges groundwater aquifers that slowly feed water to streams. In places like the Navarro, groundwater is the primary source of stream flow during the dry season. But watersheds throughout the region and state have seen declines in groundwater contributions to stream flow for two reasons. The first are changes in land use from forest and grasslands to road networks and urban development that reduce infiltration of rainfall that replenishes our groundwater aquifers. But more recently and more urgently, the problem is due to wells extracting groundwater. Growing populations, increasing water supply demands, and recent droughts have led to many farms and communities to drill wells in search of more reliable and drought resilient water supplies. And so this has led to unsustainable pumping that has depleted groundwater aquifers and their contributions to stream flow. And this is why, in part, many streams which historically flowed year-round now go dry in the summer months. So, simply put, groundwater is stream flow, rivers are groundwater dependent ecosystems, and when we deplete our groundwater resources, we're depleting our streams. We can't restore our rivers without addressing the proliferation of new wells. And while we can build projects that restore stream flow, the challenge remains that new wells are being installed all the time, negating these flow restoration efforts and worsening the crisis we're trying to solve. And so there are two existing regulatory structures which are trying to address this and achieve sustainable groundwater management across the state. The first is California's Sustainable Groundwater Management Act. I'm sure many of you in this group are familiar with it, but it was passed in 2014, enacted in 2015, and required that all of the groundwater subbasins shown on the left of this slide implement groundwater sustainability plans to achieve groundwater sustainability by 2040. So, what does achieving groundwater sustainability mean? It essentially means avoiding these six undesirable results shown on the right to all beneficial users. And within the context of um, environmental considerations, the sixth, the rightmost impact, the depletion of surface water, interconnected surface waters due to groundwater pumping, is one of the hardest and one of the most important for us to get right. And so, as defined under Sigma, groundwater dependent ecosystems are these ecological communities of species that depend on groundwater emerging from aquifers or occurring on groundwater occurring near the ground surface for some or all of their water needs. And within the context of Sigma, we often split these GDEs into two buckets for implementation considerations. The first is phreatophytic vegetation. So that's deep-rooted vegetative species that use groundwater for some or all of their water needs throughout the year. And the second is what we're going to focus on today, which is, in-stream aquatic species. And, we're going to kind of talk about sustainable groundwater management, stream flow depletion impacts, and well ordinance revision efforts later through the lens of, protection for salmonids. Of course, there are other species that should be considered in this bucket, but that's just kind of what we're currently talking about today. And so Sigma requires that all beneficial uses and users, including groundwater dependent ecosystems, are considered in the development and implementation of groundwater sustainability plans. And in particular, groundwater managers need to assess whether their sustainable management criteria, the way they manage groundwater in their subbasin, may cause adverse impacts to beneficial users. And so just to kind of reiterate the fact that several undesirable results in Sigma are related to groundwater dependent ecosystems, but really what we're going to focus on today is these in-stream aquatic species circled in the figure on the right and the depletion of interconnected surface waters due to groundwater pumping. So Sigma, addresses a large part of the state, but it's also important to note areas where Sigma doesn't apply as a regulatory requirement. You can see here on the right that there are roughly 60% of the state, 60% of the state isn't covered by Sigma. And when you focus on the watersheds that we know are a high priority for salmon and freshwater biodiversity, Sigma basins don't address many of these important areas. And many of these watersheds are home to rivers that also don't have the water they need to support listed fish species. And so, where Sigma led to the first regional efforts to sustainably manage groundwater extraction, a recent series of court cases has established new requirements to manage groundwater for public trust resources. And that's the second regulatory requirement we're going to talk about today. The precedent-setting 2018 Scott River decision established new requirements for all counties in the state of California that they must ensure that their permitting of new wells is done in a way that's protective of public trust resources, including stream flows needed for fish and wildlife. And so, shortly after this ruling, Sonoma County was sued over the impacts their well ordinance had on depleting stream flows in the Russian River watershed. This prompted them to update their well ordinance, which was completed in 2023. Santa Cruz County also initiated a process to update their well ordinance in response to this new requirement, which was successfully completed in 2025. And the completion of these well ordinance revisions is beginning to result in increased protections to public trust resources across the state. And we're seeing many counties scope how they might be needing to address this regulatory requirement in the future. However, TNC and partners actively participated in these policy and technical advisory groups that led to these well ordinance revisions being completed, and these efforts were not easy. Absent clear guidance from the state, counties have really been on their own to understand how they need to address the impacts of wells and protect stream flow, fish, and other public trust resources. And so, to address this challenge, not only from the lens of our the health of our rivers and salmon runs, but also for water security of our farms and communities, the Salmon and Steelhead Coalition recently published this guidance report based on our experience working on well ordinance revisions. And I should just pause to say that while this is talking about public trust resource considerations and well ordinance revisions, the underlying science and many of the underlying same regulatory requirements that are required in public trust resource considerations are required under SGMA. And so these are two parallel work streams that really require coordination to implement successfully. Many counties and permitting jurisdictions that are required to update their well ordinances will have SGMA basins within them. And so just to highlight that the underlying science is the same, many of the policy recommendations are the same, and that just these these efforts need to happen in collaboration in order to be successful. And so this report provides principles and guidelines to help counties and groundwater managers undertake a transparent and informed process to understand the risk of permitting new wells and to develop a protective well permitting framework. I'm going to go through each of these 5 steps pretty quickly, but there's not really time today to go over it in detail. And so to learn more, I just encourage you all to visit our website and download our report, and we'll provide the URL at the end of the presentation and put it in the chat. So the first recommended step is for groundwater managers to identify public trust resources that occur within their jurisdiction, where stream flow and groundwater dependent wildlife or ecosystems may be at risk of negative impacts from groundwater pumping. And so there are a number of databases that can get groundwater managers started, whether it's looking at listed threatened and endangered aquatic species or in-stream species with an identified connection to groundwater. These are all good places to begin to map out the sensitive resources that the frameworks need to protect. And then the second step is probably very relevant and of interest to this group, which is to identify protective stream flow thresholds that preserve ecological function. And so the goal here is really to identify thresholds that, if exceeded, would be expected to cause adverse impacts to the previously identified public trust resources or groundwater dependent ecosystems. And I'll just maybe like pause here to say to this group that this step and much of this framework really wouldn't be possible without the previous foundation and resources that the California Environmental Flows Framework has been developing. These resources are really valuable to our understanding of ecologically functional flows, and the toolkits like the functional flows calculator or the natural flows database are actually really critical steps in our system-wide understanding of surface water, groundwater interactions, and really lay the groundwork for our ability to assess impacts of stream flow depletion due to groundwater pumping. So that is just to say that all of these tools are going to be really critical to identifying these protective stream flow thresholds and conservation goals. And there also may be, existing local studies on recommended minimum in-stream flows that can be used and just basically help develop a watershed or regional approach to the ecological goals of each of these permitting frameworks. And so once protective stream flow thresholds have been identified, the next step is to determine if current stream flows meet those thresholds in all year types. But in particular, we'd be concerned with dry years. And so resources for evaluating existing stream flow include gauge data available by USGS or CDEC. Absent existing data, additional analyses might be needed to estimate stream flow conditions based on spot measurements or modeled analyses. And it's also really important that existing stream flows are understood in the context of existing water rights from a surface water groundwater interaction perspective. So, and is because a significant portion of stream flow may already be allocated or being used, such that the permitting and addition of new wells could undermine the reliability of water supplies for existing surface water users. And so, when groundwater managers are considering these types of questions in their analysis, things like the board's Cal Water's water rights database is a good starting point. And then finally, in this step, when we're understanding the impacts of, we need to have a comprehensive understanding of both surface water conditions and existing groundwater use. And so, in order to understand the depletion impacts of existing wells and move to a place where we can assess future wells and risk of additional stream flow depletion, integrated surface water groundwater models or some groundwater modeling framework will be needed to estimate existing stream flow depletion due to groundwater pumping. And this step and kind of the step four are some of the most challenging because groundwater models are very expensive and time consuming to develop, and groundwater data can be really limited. Our understanding of groundwater dynamics can be limited. And so that has been the focus of some of the work we've been doing, some of the work we're continuing to do with David under Seth, is to develop these new modeling tools and approaches to help counties assess these surface water groundwater interactions. And so moving into step four, we begin to shift from the identification phase of our approach to the evaluation phases, which is to pair our understanding of existing conditions with groundwater modeling approaches to assess future stream flow depletion risk. And we really recommend that this stream flow depletion impact modeling is done through a unified modeling approach. And I use that term unified modeling approach to describe that there may be different times where it's appropriate to use different groundwater models to assess stream flow depletion risk. For example, if a well-developed numerical model exists in a subbasin, this can be a great starting point to understand surface water groundwater dynamics at a local scale. And on the right here, we kind of have one example of this. This is a case study, a USGS case study from Nebraska, where they simulated how groundwater pumping impacted baseflow contributions to surface water streams after a 50-year model runtime period. And you can see in the warm colored areas where a majority of pumped water from those regions was sourced directly from stream flow depletion, a reduction in stream flow. And it's these types of modeling tools and modeling exercises that can help enable the development of decision support tools for integrated water resources management considerations. But I also just want to recognize that there is a high level of technical expertise and cost with the development of these models, and groundwater managers and local environmental stakeholders across the state may need additional low cost, low complexity tools at their disposal. And so that is certainly a consideration in our future work where we're helping understand what low cost, low tech decision support tools can be developed for stakeholders at the subbasin or county scale. And then the final step is really to aggregate all of the things you've done in the first four steps together and develop a revised well ordinance policy and permitting approach, or a revised SIGMA implementation approach with respect to stream flow depletion considerations. And so you're taking all these data sources, these tools, and this framework to develop a policy that will comprehensively assess the risk of impacts to stream flow due to groundwater pumping. And this process is really a beneficial thing to do because it results in a variety of useful information and tools that water resource managers will be able to leverage going forward. Throughout the process, in steps 1 through 5, you'll develop maps of public trust resources and sensitive species. You'll develop, an in-depth understanding of your ecological stream flow threshold goals. And it'll set up a framework to assess future groundwater development in a manner that's protective of public trust resources. And so this is our recommended workflow from this guidance report. But I'm guessing that many of you might have questions about what some of these steps look like in practice. And so the second half of this presentation is going to shift gears a bit to some real world examples of how we model stream flow depletion due to groundwater pumping. And just recognizing again that we recognize that this is a high technical lift, and we're really thinking about how to build decision support tools that can be easily accessible to all stakeholders when considering public trust resource considerations or SIGMA implementation going forward. And I guess kind of like before I hand it over to David, I've kind of said a lot of this, but groundwater managers really need support. In order to do this right, we need these things like stakeholder participation, statewide guidance, potentially like standardized well ordinance revision processes, and then low cost, easily accessible technical resources for all stakeholders in the process. This is going to require funding and technical assistance at the statewide level, both with respect to well ordinance revisions and SIGMA implementation. And I would just say stay tuned on how our groups are helping to push all of these priorities forward. So with that, I'll kind of hand it over to David for the second half of this presentation.
Thank you, Nick. I don't have the presentation here in front of me. Nick's in charge, so I'll cue you, Nick, to move things forward. And it looks like we have already a few really good questions in the chat, so maybe we'll keep those in mind, and I think maybe at the end we'll have time to address some of those. So yeah, I really wanted to focus on kind of step 4 of Nick's proposed workflow and really thinking about what it takes to develop these groundwater availability maps, resources and tools to go about the state to different counties or municipalities or even individual farms and predict and understand how pumping and groundwater dynamics might impact stream flows. And I wanted to start this with kind of like a physiographic lens and really break the state up into 2 distinct zones. And one is kind of the places where we are already starting to think about how to manage groundwater sustainably. That's the SIGMA basins. Most of these, or several of these, are pictured on the left. I think that's a SIGMA district map, right, Nick? And all of these locations are very flat, typically ag oriented, and they're depositional environments. So they're not kind of like the eroding mountain environments that we see on the right-hand side. And these are places where we at least currently don't have a concrete statewide framework for doing any kind of sustainable groundwater management. But groundwater is present and very important, and I'll get into that in a second. And I just want to highlight the overlap between the map on the right and the map in the very center, which identifies all these priority watersheds for salmonid and freshwater biodiversity. And so, understanding how pumping and wells might affect stream flow is really important for answering some of these like conservation related questions, especially as they pertain to salmon. Next slide. And this is a paper written in 2022 by one of Nick's collaborators, Sam Zipper, where Sam points out that streamflow depletion, or the way that wells affect streams, is not necessarily something that can be measured directly. It's not like we have one watershed and another copy of that watershed, and we pump one and we don't pump the other, and we have this kind of like real world controlled counterfactual where we can say exactly what the impact of the pumping is. Some pumping studies have been done on really small scales, but when we go up to larger watersheds or entire basins, it's really hard to constrain flow depletion without having a model to ask this counterfactual question. Next slide. And so this brings us to, kind of with all that context, how do we choose the right groundwater modeling tool for the job, whether it's we're in a depositional valley environment like the Central Valley, whether we're up in the hills in the Sierra or the Coast Range. How do we decide kind of what representation of groundwater in a modeling framework is appropriate? And how do we get these tools kind of available and on the level for people that are out there making decisions, or trying to decide where to drill, how much to pump, et cetera, to meet management objectives or sustainability goals. Next slide. And so just to briefly review what streamflow depletion is, I think we've been kind of hinting at it throughout the presentation, but I wanted to provide maybe a slightly more concrete picture of what's going on. When we say streamflow depletion, we're really talking about asking the question, if I had not pumped water from a collection of wells, say in a field or in a watershed, what would the stream flow have been without that pumping? So it's asking this counterfactual question. And so you're really asking, to quantify depletion, to quantify, how much higher stream flow would have been if you hadn't pumped. You really need a modeling framework to explore that what if scenario. And so the ultimate goal for most of these models is to come up with a picture like you see on the right, where you have some kind of physical system, a groundwater system with a stream. You have an observed hydrograph, which is that blue line. Maybe you have a stream flow gauge and a catchment that's pumped, and you see what it actually looks like given the pumping that has occurred. But what you really want to know is, what's this dashed line? What would the stream flow have been in the absence of pumping? And ultimately, how can we quantify this difference in water volumes between the pumped and the unpumped scenarios? And that's the ultimate kind of objective for most of these modeling exercises, at least to kind of like a first order approximation. Next slide. So let's zoom in particular really briefly on choosing the right tool for the job, or choosing the right tool for your system. Advance it once, Nick. And we're going to focus on just really one slide on these depositional kind of valley environments that you might see in a Sigma basin. Next slide. So honestly, Nick would be better at presenting this slide than me, because he has done a lot of work with Sam Zipper to develop this collection of modeling tools that they call analytical depletion functions. And these are really simplified, physically based hydrological models that you can really kind of write down in a single equation and solve in a pretty straightforward way, almost algebraically. And they let you kind of determine how stream segments are impacted by a collection of wells. And they make some really simplified assumptions, but useful assumptions in a lot of cases, about how that groundwater system looks. So the picture on the right is a good schematic for the types of environments where these ADFs, these analytical depletion functions, might be applicable, where you have a thick aquifer with a fully penetrating well that's being pumped. There's not really any significant topography. The base layer at the bottom of the aquifer is also flat. The aquifer itself doesn't have a lot of slope, except within the vicinity of wells, where you see a kind of cone of depression. And all of these physical attributes are necessary simplifications to make the ADFs work in practice. And so Nick and Sam, like I was saying, have really taken this approach on the road and come up with a way to generalize the kind of single well picture that you see on the right to a collection of wells distributed throughout a watershed or throughout a stream network. And directly answering the question, like if I choose this stream segment right here, how does this large collection of wells in my study area affect stream flow generation and absence or presence of water, for example, at a particular location. Next slide. Next slide. But my world and background has been really focused on these upland environments, hilly places, hill slopes, where instead of kind of depositional flat valleys, we have eroding landscapes, streams actively incising into bedrock, creating hill slope relief, and largely dominated by bedrock. This kind of incision of streams and the development of topography leads to bedrock that's very close to the ground surface. Typically in upland environments throughout the state, soils are 1 to 2 meters thick at most, which means that a lot of the groundwater storage, the water storage that we care about for stream flow generation is within that deeper bedrock. And in addition to that complexity, there's the topographic complexity and all these other attributes that I'll get into that make the modeling question or choosing the right tool for the job a little different than we might uh, need to use in some of these valley environments. And so here's a nice transition, Nick. Here's a picture of a hill slope in an upland environment. And I like to think of this as kind of semi-representative of what you might find if you were able to go to a random slope in a forested environment in California and kind of peel back the surface and ask what lies beneath. And what you often see, and what we have seen directly with drilling campaigns and geophysical monitoring and measuring across the state at a collection of sites, several in the Sierra Nevada, several in the Coast Range, is a picture like this where you have typically really thin soils underlain by a relatively thick weathered bedrock layer. And all of you have seen this if you've gone driving in the hills and you see road cuts where highways kind of pass through rocky areas. You'll often see a lot of this kind of, exposed profile where you see the really thin veneer of soil overlaying a lot of like really crumbly, crappy, fractured rock. And this is where the groundwater that feeds streams live. So typically, several meters, if not tens of meters below the surface, you find a groundwater layer that's perched atop a fresh, relatively unweathered, unphysically altered by rain and physical erosion, unweathered bedrock layer. And this kind of acts like a bottom boundary to the system where we have trees rooting in the overlying unsaturated soils and weathered bedrock. They transpire, they use water. Any rainfall that falls or snowmelt that kind of enters the subsurface in these landscapes in excess of the root zone's ability to store that as unsaturated storage will drain as recharge to the groundwater. Groundwater is typically really dramatically sloped towards streams and it flows laterally and supports not only base flow, but also most wet season flows that we see too. So unless you have unless you have a reason to believe otherwise, this is the picture that you should have in your mind when you are asking what's beneath your feet and you're in a forest. Next slide. And this is just a collection of my general observations of hill slope groundwater systems, the ways that they're unique. And I'm not going to necessarily read them all out, but some of these are, distinct and quite different from the valley environments that I talked about earlier. We have significant diversity in like the depth of groundwater. It's often deepest at the ridge. That's for physical reasons. It often resides within fractured weathered bedrock as opposed to soils. We know that this deeper bedrock groundwater is the primary driver of stream flow, not just during the dry season, but also during wet periods. And finally, it's also really highly responsive to rainfall. And so at our locations or observational sites, we see that groundwater not only responds on the kind of timescales of individual rainfall events, it tracks and clearly drives flow as well. So it's not a static, slow moving thing. It responds on it kind of has similar dynamics to the flows that we see in our streams. Next slide. And I don't have my notes in front of me, so I might not get all this, but the question is just that where I'd like to kind of go over with the group is how does this groundwater behave? How does it drain? How does it feed streams? And to answer this question, I want to take a little quick detour to talk about an ecological mystery in Mendocino County, California, where satellite reveals this dramatic shift in vegetation cover as you go from west to east, from dense evergreen mixed conifer hardwood forest to the west to white oak, Oregon white oak, Quercus garryana, savanna to the east. And this is outside the fog belt, and it's about 20 kilometers inland. And climate analysis shows that this kind of ecotone or shift in vegetation can't be explained by changes in rainfall or temperature. Additionally, we've done a lot of work to look at land use records, and so it rules out anthropogenic explanations for the shift in land cover like grazing or logging. Next slide. So things start to come into focus when you look at this picture when we overlay a geological map, where this ecotone coincides with a boundary between two belts of the Franciscan Formation, which is a geological complex in Northern California. On either side of the fault, different rock types have led to very different subsurface structures. Next slide. There it is. In the coastal belt to the west, we have a thick subsurface profile comprised of thin soils, overlying fractured mudstones. And this is a really common feature in mountain environments, these deep fractured weathered bedrock layers, like I was saying. And this thick subsurface stores seasonally really large volumes of water in the root zone, which is primarily bedrock also, supporting dense conifer broadleaf forests, like I mentioned. And groundwater in these profiles supports and sustains really elevated summer dry season base flows. Next slide. One more. There it is. The Central Belt geology to the east, also I'll maybe refer to it as the melange or the Central Belt, features a really thin profile underlain by a geology with fracture-resistant clay-like material that is perennially saturated at depths as shallow as 2 meters. And so that means that at 2 meters, water is essentially stagnant. It's stuck in low permeability material. It's not available to trees. It's not available to drain to streams. Here in the wet season, this thin subsurface rapidly fills. Runoff occurs as primarily saturation overland flow, and that means that groundwater literally rises to the surface. Any additional rainfall in excess of that kind of storage in the profile leaves as rainfall or leaves as stream flow. And this subsequently or consequently leaves less summer storage in the subsurface for streams and vegetation. And so this geology is really what explains this shift in vegetation that we see as we go from west to east. Next slide. And just briefly, I'm not going to talk about all this. I'm mostly presenting these slides to promote a couple of papers that you can go look at if you want to read more about kind of all the ins and outs of hydrology in these two places. These sites really represent two end members, I think, that nicely illustrate the primary mechanism by which groundwater mediates runoff. At this coastal belt site, we have lateral flows and deep bedrock that moves through fractures and emerges in the stream through a collection of seeps and springs, typically in kind of bedrock seepage faces near the stream. And then in the central belt site, the melange site, we have thin profiles that rapidly fill up. You can see that in the little zoomed in set there, where some water moves in the subsurface as this shallow subsurface flow to the stream. The rest of the water that reaches the stream occurs as saturation overland flow, which I defined a second ago. And in both cases, it is, even though these places look very different, it is groundwater that mediates all aspects of the flow regime. So these are a couple of plots, just the top one on a linear scale, the middle one on a log scale of stream flows. So those are the same time series. They're just scaled differently, so they accentuate different parts of the hydrograph. But you can see how the low storage, thinly weathered sites in the central belt have really high peak flows. Flows are very responsive even to initial rainfall events at the start of the wet season. Peak flows are 2 to 3 times as high as the coastal belt sites. Both of these sites, as you can see in the bottom, have pretty much identical rainfall season to season. They're very close to each other. And then in the kind of center figure there, you see the difference in primarily the flow recession and base flows, where you have a perennial cold water stream in the high storage site, flows that continue throughout the summer, even into October, November, December, before, if rains arrive late, the stream keeps flowing. And in the central belt sites, you typically have ephemeral streams that dry up by June or July at the latest. And the flow recession is very rapid. So very different, kind of seemingly very different hydrologies in a lot of ways. But ultimately, all of this is explained by what the groundwater is doing. Next slide. And I just want to point out that although those sites I was talking about were, very small kind of hill slope studies where we were observing everything and coming up with these conceptual pictures, they really matter at the larger scale. So the Eel River watershed, where these are located in Mendocino, is actually a kind of a geological hybrid. It's comprised of a bunch of smaller subwatersheds that are either coastal belt or melange or some mixture of those two. And so this manuscript I'm citing here really goes through and shows how some of these geological hybrids kind of behave the way you would expect as a mixture of these two end member cases. And so this very small site-based study of geological influences on ecohydrology has implications for larger watershed scale understanding. Next slide. And all of this kind of leads us to how back to this step 4 in Nick's process, coming up with resources and models and tools for people to use, not only in the valleys, but also in upland environments. And so this is this so-called hill slope Boussinesque is a simplification of the groundwater flow equations that incorporates kind of the essential features of groundwater in upland environments that we would like to include in a stream flow depletion or pumping model. It's simple enough to kind of incorporate realistic physics, but it's complex enough to pull in all the aspects of upland groundwater systems that we think are important for getting flow predictions and stream flow depletion predictions correct. So these include things like dramatically sloping water tables, complex topography, sloping impermeable layers, and streams that form kind of a boundary on the hill slopes themselves, and are really the kind of surface manifestation of what the groundwater and the hill slopes are doing. So that's, I guess, just to summarize that, that's sort of the direction we're heading in these upland environments. Next slide. And that brings us to, go ahead, Nick, next slide. And that brings us to, I want to credit this picture to Nick, who had this idea to really think about, what's the right level of complexity, both in terms of the physics and the practical, kind of cost, difficulty, person hour considerations that go into developing hydrological models, where we have really complex models, numerical models, like, say, a team of USGS scientists would develop for, say, the Russian River, that we trust to help us predict flow depletion, but are not really necessarily straightforward to develop on the fly, or at a small site, or in places or contexts where we don't have significant funding or technical support. And so we're focused on these two cases on the left, the analytical depletion models depletion function models that Nick and Sam have developed, and then some of these hill slope boost nest models that really kind of bring in a few additional features that we need to capture the essential features of hill slope groundwater systems in upland and eroding environments. And so we're working on really coming up with a kind of a suite, a collection of different tools that can be applied in different locations to, to have the right tool in the right context to predict and better understand flow depletion throughout the state and its, throughout its diverse environments. I think that's everything. There's a lot of questions, so I should probably get to those. Thanks, everybody.
Yeah, thank you, Nick and David. So we can go through the chat. Well, I don't know, Chris, what do you think? Should we go through the chat or should we ask people if they have any live questions?
Sure, yeah, we can go through the chat.
Okay. So I'll just go in order. Kathy Buchanan asked, how can there be groundwater sustainability when industrial agriculture and water bottling companies do not have any limitations on how much groundwater they're able to use, especially with water wells that are already established? Consumptive uses are not metered, which includes the vineyards. Um, that's a very complicated question, but I don't know if that's like what David and Nick's presentation really was directed at today. But I think
But we
you
hear
know,
you, Kathy.
yeah, we're with you. Uh, and it has to like kind of lean back on the Sigma process and water rights to um, handle. So that's probably not a satisfying answer, but I'm gonna actually kind of probably weed through these and look for more of like the technical questions since we have David and Nick here. Um, this is when asked if there'd be a model that includes abandoned mines or orphaned oil wells. I don't know that continue to affect groundwater levels. I'm not familiar with that. David or Nick, do you have any insight on that?
I don't. I mean, I can say that, if water is not being actively pumped from these, there's not, in a simple sense, and if they're not actively like draining, say, to a stream, I wouldn't necessarily, expect a mine to really influence groundwater. That's if there's sort of just like static voids in the subsurface that are not being water is not being removed from them actively. But as a general question, I'm not sure. I've not really looked deeply into that. I know that would certainly be a problem in some of the foothills of the Sierra, maybe some of the wells that we found in parts of the eastern parts of the Coast Range that are still out there that do have some water seepage and groundwater loss, but at least in my experience, it's been kind of small to observe, but I don't know a lot about it. Maybe Nick knows more.
I don't know a lot about it either, but the one thing I would just flag is like well location and abstraction databases are a really big gap still across the state. And it's like often the well location data sets we have are relatively coarse. And so we're pursuing some, technical advancements in how we can improve those models and maybe considerations for abandoned wells would come into play later in that process. But right now we don't have anything explicitly thinking about that in our workflows.
I'm gonna pull out this question, like how do we address the fact that a lot of watersheds have no hydrology data or flow relationship data, let alone like surface water groundwater model interaction. So I guess the question here is like how do we assess streams that don't have data?
Good question. I mean, I'll address it maybe from like a 10,000 foot view, and then David maybe has more like model specific thoughts. With this kind of management framework that we are proposing, that kind of takes you from step one from the beginning to the end. And so it will let you assess and acknowledge those data gaps and put you on a plan to fix it. and acknowledging that when we have data gaps, we have uncertainty, and that to some degree you need to follow things like the precautionary principle, where if you don't have the data to show that you're not having an impact, it might be more beneficial in the short term as interim management to assume you are having an impact.
I'll just throw in that this is something that we deal with a lot in watershed hydrology, um, where we, especially in upland hill slope type watersheds, we maybe have a couple of gauges. Most places we don't have gauges. The good news is that there's a lot of good physical reasons to believe that, if a watershed has a particular geology and a particular forest cover, um, it it is likely to behave in a way that's comparable to an observed watershed that has that same geology and that same vegetation cover. So there's a lot of ways that we can leverage the kind of transferability of physics to, take an observed watershed and use what we know about it to make predictions in poorly observed or sparsely gauged places. And so that's the like big question in this field of subfield of my world that's called prediction in ungauged basins. Um, I would recommend looking at that Salmonid paper that I cited, where we, kind of zoom in on these two intensively monitored sites, and then we zoom out to the larger scale, the Eel River watershed, and ask, are the observations that we made at the small scale consistent with these geologically hybridized watersheds that we see throughout the eel? And there's a lot of consistency, which supports this, kind of you'd almost call it like a philosophy, like treating hill slopes like atomic units. And if we kind of know how one of them behaves, we can extrapolate how all of them behave together. That's kind of like the approach. And, it's there's certainly like challenges and drawbacks to doing things that way, but that's at least in like hill slope watersheds how we approach it. But as generally speaking, it's a great question. If you don't have data, then you'll never be able to do something like validate a model and say for sure whether it's working, getting things right for the right reasons. It's always going to be a challenge.
Thank you. There's a couple questions about just climate change considerations in this type of modeling. A few about decreasing like snowpack levels and that type of thing. Do you have anything to add about climate change and change over time?
I'll say that at least in the Busanesque modeling that I'm working on right now, climate comes in a few different ways. One is there's an explicit, I didn't get into the guts of the modeling, but there's an explicit representation of vegetation water use. So hotter, drier futures would impact how vegetation access water, how much water they access, tree water stress, those types of things. And that would ultimately change groundwater recharge and, how frequently and how much our also groundwater systems are kind of recharged or filled back up every year. And so including some dynamic terms that account for evapotranspiration. That also addresses another question in here I saw about, dealing with deforestation upslope, in a sense that, that's related to this climate question. It's really like, how do the dynamic pieces of our watersheds respond to perturbations like a dry year, like removal of trees? And a lot of that results in just changes in how water is stored and removed by vegetation. So we're doing our best to put in at least the big pieces of that puzzle into these models. I don't know if Nick has other thoughts on how we incorporate that.
I think that's a good answer, David. I don't have too much else to add other than I think folks in the Sigma world are still grappling with how to implement climate change considerations into Sigma requirements and are continuing to kind of work with DWR as guidance comes out to better understand to what degree is necessary to incorporate like climate change scenarios in these modeling tools.
We have a question about whether or not the analytical and simplified tools that you kind of discussed can be used to evaluate how managed recharge can improve stream accretion in baseflow conditions.
It's a really great question. So theoretically, the analytical models, you can essentially reverse the sign of your pumping to create a recharge signal, and that would be possible to kind of understand the lag time of potential stream flow benefits. I will say it hasn't been, to my knowledge, been done in practice or like tested to see how well it works. We did some modeling in the Scott Valley, looking at comparing the analytical approach to existing numerical models there from a pumping aspect. And I think like on my mind, and a great next step in some of that work would be to investigate like how well analytical models can represent recharge dynamics and timing. So it's definitely on our minds and something to think about. I think I'll let David answer. It's definitely possible in those more complex models. It's just maybe more of a question of how realistic is it to induce managed aquifer recharge on like a steep hill slope.
Yeah, that's why I'm not going to answer it. We probably won't be flooding hill slopes. I mean,
Yeah.
except in cases where we build new dams. But yeah, that's a good answer, Nick. Like my first thought to that was, yeah, just reverse the sign on the pumping and make it smaller. That's
Yeah.
kind of simple and it's probably too simple in some cases, but it would maybe be useful to try and think about.
We have a question about if whether or not this groundwater modeling answers the question about like the number of wells or the capacity over time, um, about cumulative effects worsening, the cone of depression type of situation. Um, I don't know. Yeah, Nick, I feel like this kind of lands in that well ordinance category.
Right. So I mean, both modeling approaches can look at cumulative impacts, and that's kind of, what we really wanted to get at in some of these stream flow depletion considerations. So like what are existing cumulative impacts across the landscape, and then what are potential new impacts when thinking about permitting another well. I will say that both regulatory frameworks have some limitations with respect to existing cumulative impacts. Trust resource considerations are only required to consider the impacts of new additional wells on a system, so not to actually uh, reverse any impacts from existing cumulative impacts. And then within a Sigma context, there's the piece of Sigma where groundwater sustainability plans are required to not let conditions worsen compared to the 2014, 2015 baselines that existed when the law was passed. And so, depending on the geography you're in, you may have significant ecological function being altered already. And so in that case, sigma is less effective for requiring the preservation or the prevention of stream flow depletion impacts. But I think like in a lot of these coastal watersheds and within sigma basins that have functioning flows to some degree, there is like opportunity in both of these regulatory frameworks to protect and establish ecologically protective thresholds. Hopefully that answers your question.
Okay. So I think David and Nick can weed through some of these while the next presentation is going on. But real quick, does anyone who didn't put a question in the chat have anything they want to ask? We've got a few more minutes in our agenda for questions, but I wanted to open it up to anyone that wanted to ask a live question.
And we like live questions.
Uh, Norman?
Can you hear me?
Yes.
Uh, that was a great presentation, you guys. Very difficult topic, as you pointed out to begin with. You can't actually measure it most of the time. But I was noticing, Nick, I think in the slides I saw that in your kind of valley topography model, you have like a less permeable layer that's around where the aquifer and the stream meet, I think. And I think that's thought to be the case typically from a hydrologic point of view. And that raises lots of difficulties in its own, like how thick is that and how impermeable is that, or less permeable is that? And then, David, I didn't see anything like that in your hill slope model, which may be more appropriate, I guess. There's never time for an accumulated silt and sediment, perhaps there. But I was wondering if both of you could talk about if it doesn't exist, I guess. David, you can just say so. But Nicholas, I was wondering if you could elaborate more on how you handle that. Seems like another hurdle to overcome in terms of uncertainties.
Yeah, it's a great question. And so it depends, Norman, on what analytical model you're using in the like spatially distributed analytical modeling framework. And so, like the Glover and Balmer, kind of like the oldest stream flow depletion analytical solution, doesn't have that semi-permeable or semi-confining stream bed conductance layer.
Right.
Later models do develop that, and so then it's certainly possible to incorporate it, but it becomes another question of like data quality and parameterization, and do you have um, sufficient data to change that parameter across your watershed? And people, there's a pretty big body of research looking at trying to the applicability of doing that, like how sensitive a parameter stream bed conductance is to gaining and losing reaches. And so it's certainly possible. We've been kind of like starting simple and then building up to where we need to go. And I'll let David speak to the Hillslope models.
Yeah, that's a really cool question, Norman. You're right that I don't think the sort of transmissivity of the stream bed in upland watersheds plays a really important part in kind of dictating or influencing the dynamics of a hill slope groundwater table, it being steeped and underlain by a bedrock slope that kind of pretty quickly as you move away from the channel rises to an elevation above the channel itself. Um, but it really does matter once you're in the stream and you're asking the question for a given amount of discharge, how much of that discharge is actually above the surface and how much of it is below the surface? So, beds or streams commonly in mountain environments typically kind of have these like riffle pool sequences where you have like an alluvial pile and then following that you have a scoured pool and then you kind of have that alternating sequence. And so you can have, for a single stream flow discharge value, water flowing in those deeper scoured pooled areas and water that goes subsurface in some of those more alluviated reaches. So although that's maybe not having a big impact on the overall like kind of hill slope groundwater dynamics, it really does change sort of how you really the manifestation of like a given value of discharge in terms of surface water availability once you're in the stream. And that's something that my group is working on actively right now, really like trying to go throughout these mountainous places and quantify the conductivity of the hyporheic zone, how much water can be conducted through the subsurface bed material, and how does that influence the presence or absence of surface water and flow disconnection, that kind of thing. It's a good question. It's very much like an active area of research. I'll put a link in the chat to a paper that just came out from by a friend who um, updated a pretty widely used hydrological model to kind of start thinking about that a little bit more. That's a good question.
Thanks.
Okay. Well, thank you guys for all the great questions. And if you have anything else, please feel free to put it in the chat. But we're going to hand over the meeting to Christian to talk about using CEF to inform sustainable management criteria in groundwater fed streams in the Napa Valley subbasin. So take it away, Christian.
Thank you. Trying to remember how to share screens in Zoom. Um, Thanks a lot for inviting me to give this talk today. I share. Hold on. I'm trying to talk and make this work at the same time, which is probably a bad idea. So please bear with me for 1 second. This is the, can everyone see my screen?
Yeah.
Great. This is the, I'm really lucky. This is the
Oh,
second
sorry.
time in the
Can you
last,
swap your view? It's in the,
oh,
we don't
it's,
hear.
oh,
Yeah.
it's got the wrong one. Oh gosh, it's gonna be,
Yeah. If you go to display
yeah, I
settings.
got it.
Okay.
I,
There you
but,
go. Yeah.
okay. Well, now you can't see the next slide, so everything will be a mystery. This is the second time in the last week I've given a talk after Nick. And so he's covered a little bit of the stuff I'm going to talk about in a much more eloquent way than I will. I want to I guess I'm just going to move forward. I just wanted to say that and really enjoyed the previous talk from Nick and Dave. What I'm going to talk about today is using the California Environmental Flow Framework, or CEF, to inform sustainable management criteria for groundwater fed streams, it should say, in the Napa Valley subbasin. This is work that's collaborative, that's been done through with myself. I'm Christian Broderick. I'm a geomorphologist at Stillwater Sciences. Three other Stillwater folks who've worked a lot on this are Esther Adelstein, Katie Kobayashi, and Amana Russell. And many of the good parts of the presentation are their work, and any of the mistakes are probably mine. We've also been working with Ludorf and Scalamanini consulting engineers there. Have done a lot of the groundwater monitoring and modeling that we'll be relying on today. The Napa County RCD has done a lot of the habitat and fish surveys that we'll be talking about. And folks from Napa County have been doing a lot of the some water quality monitoring, and also the Napa County is the groundwater sustainability agency that's driving this work forward. So just sort of an outline of what I'll be doing. I'll be giving a little bit of overview and background about groundwater dependent ecosystems, and then the Napa Valley subbasin. Well, then I'll switch to talking a little bit about ecosystem goals and some of the struggles. Well, maybe struggles is the wrong word, but some of the work we've been doing to try and see how ecosystem goals change within the watershed based on monitoring that we've been doing. And then we'll take a look at flow ecology relationships, including hydrology, steelhead and foothill yellow-legged frogs, and then finish up with next steps. I want to say this is a work in progress, so I'm not going to be leaving you today with answers. We're still conducting this work now, but I think there's some interesting things in here that are food for thought. So this is a sort of, Nick gave a slide that was very similar to this, but just quickly to remind you, for those of you that aren't used to the Sigma world, groundwater dependent ecosystems are species or ecosystems that rely on groundwater for some or all of their water needs, and those can include the direct things directly reliant on groundwater, which are things that can tie into their roots into the system, like plants, or things that rely on the vegetation, like birds. But it also includes interconnected surface waters. Those are surface waters that's connected hydraulically to groundwater, and all the things that live in there. And so my focus today is going to be on this interconnected surface water piece. Just some Sigma basics. The Sigma world is a world of acronyms, and I'll try not to use too many of them, other than GDEs, which I'll use too much. But so Sigma, as part of Sigma, groundwater sustainability agencies are coming up with groundwater sustainability plans, and Sigma requires groundwater sustainability agencies, or GSAs, to consider groundwater dependent ecosystems when setting sustainable management criteria. And there are also ecosystems that are relying on interconnected surface waters. Each GSA must set a measurable objectives and minimum thresholds, which can change within their subbasin for, among other things, for groundwater elevation and interconnected surface depletion of interconnected surface water, which is what we'll be focusing on today. And there are um, two different levels. This is an example taken from another basin. The measurable objective is sort of where you want the basin groundwater level to be so that the basin can weather things like drought without having negative impacts or what they call undesirable results. And the minimum threshold, which is a numeric value for each sustainability indicator that we're going to use to define undesirable results. And one of the questions we're trying to answer as part of this project is, what should the minimum threshold be when considering the groundwater dependent ecosystems? And how does that change from place to place? So this is an aerial view of the upper half of the Napa Valley subbasin. And one thing I want to make clear is that the groundwater, and Nick and Dave talked about this a lot. The groundwater subbasin and the upper watershed are the watershed are two different things. That the subbasin is just the alluvial part of the basin where the aquifer is, but there's a lot of the watershed that's upstream. And in our case, the areas upstream are the place where the habitat tends to be better. These streams and the upland streams outside of the groundwater basin, they tend to be perennial, at least in their lower reaches, until their drainage area gets too small. There tends to have better bar and pool habitat, cooler stream temperatures, and that's where most of the ground things that we're going to be talking about today are, including steelhead and foothill-legged frog. That's where most of the habitat is. The Groundwater Sustainability Agency is really only has control over the groundwater subbasin, or control is probably a strong word, but and within the subbasin, the watershed's very different. You can see it's very agricultural. The Napa River itself is deeply incised, 10 to 15 feet in places, or in most places. That incision has a strong legacy for the amount of habitat that's there. The channel's relatively narrow. It contains most of its flooding, and so there's not a lot of bar and pool morphology because the width to depth ratios are relatively small. And within the subbasin, the main stem is intermittent in places. It does go dry in the summer, and other places it flows. It's perennial during most years, but most of the tributaries go dry. They're mostly on alluvial fans, and they're perched above the water table, in part due to all this incision that's happening. And stream temperatures are warmer. That arrow is to remind me to point out that in this Google Earth image I stole, you can see the largest reservoir in the subbasin is Lake Hennessy. It's small relative to many other watersheds. There are numerous other dams in the watershed, but that's the biggest one. Most of the other dams probably don't have a huge control on hydrology. That's not to say they have none. But Lake Hennessy is the biggest one, and it comes down. It joins the main stem Napa River just sort of at the bottom of this picture, down near Yountville, along Kong Creek. The subbasin supports a lot of various aquatic special status species. There's steelhead and foothill yellow-legged frogs, which is going to be sort of the focus of what I'm going to talk about later. But there's also northwestern pond turtle and California freshwater shrimp up near Calistoga. There's also Chinook salmon that use the basin. They're thought to be mostly strays from the Central Valley system. But we saw a lot of Chinook salmon out in the rivers last year, and very few the year before. So there are three basic types of flows in the Napa River. This is a very simplistic view of the range of summer flows, but rivers can be flowing. They can have what we call isolated pools, where the pools are wet with the dry riffles between them going dry, or the channel can be completely dry. That state is dependent on the level of groundwater, and so we've been trying to ask this question of where are the transitions between these different flow states occurs, when they occur, and how do they align with water requirements for target species. A simple geomorphologist view of the world is that I haven't taken a lot of biology classes, but what I did learn was that fish need water, and so when the channel's dry, it's very difficult for fish to do anything but flop in the sand. But they the way we're thinking about it is that they need the opportunity to grow large enough to go somewhere where it's not going to go dry. And we've been one of the main question we're trying to get at is that what groundwater level or surface water depletion rates do impacts to the listed species occur within this framework, and where would we set our minimum threshold based on local conditions to not have negative impacts due to groundwater usage. So in order to answer that question, and as a way of asking it, we're using the California Environmental Flows Framework, which this group is sort of the waving the flag for. And there's a lot of appeals to this approach. It's a systematic approach to assessing in-stream flow criteria. It's got a lot of there's a lot of steps and guidelines that are well thought out, but it's not so restrictive that you can't use different models if they are available. It's based on setting ecosystem goals and biologic requirements. CEF can be used at different levels of detail for different flow components. Our focus is going to be on the dry season low flow because that's the key groundwater linkage. We account for non-hydrologic factors such as changes in habitat. It's been used by state agencies a lot, and it can be used to inform sustainable management criteria for the things we're interested in. As I said, we're focusing on dry season low flow. So the first thing you need to do when you're doing CEF is to define ecological management goals, and that seems like it's a relatively simple thing to do. We want, on a sort of broad level, you can ask yourself, you can have a goal of protecting or improving aquatic habitat for listed species, something like that, which is the broader goal. But really, the goals change based on different locations within the watershed. Different locations with the watershed function differently, provide different habitat, and so we needed to go out and do some monitoring to sort of tell us what was there, to tell us what was there and what's using these different spots in order to set these goals. So we using a scoring system that based on the available hydrologic data, the number of special status species life stages that used a given site, life stages and number of species, and other factors such as whether there was stream restoration or something similar to rank these sites. And from that ranking, we came out with these 6 sites that includes 4 sites in the main stem Napa, ranging from Calistoga in the north to Oak Knoll at the south. 2 of these sites are at USGS gauges, the Napa River at St. Helena and the Napa River at Oak Knoll. There's 2 tributaries, Sulphur Creek and Bale Slough. Bale Slough was recently restored in its lower sections, and Sulphur Creek is one of the largest tributaries in the basin that has a very high sediment load and had supported a population of Putilia-legged frogs for some time. We did 2 years of surveys. We've done 2 years of surveys to date, 2024 and 2025. Both water years were sort of below average precipitation as measured at the southern part of the basin near the town of Napa. But in the northern half of the basin, 2025 was much wetter than 2024. There was an atmospheric river that came through in November that didn't really get down to the southern part of the basin, but there was a lot of precipitation in the northern part. So 2020, functionally for the stream, 2025 was a wetter year. We've done a lot of monitoring in partnership with the RCD and Napa County and LSCE. We've done visual encounter surveys for amphibians and reptiles in both years. California surveys for California freshwater shrimp within their critical habitat near in the reach near Calistoga. We're doing riparian bird surveys with bird call recorders and some on-the-site observations. And we've also mapped the health of vegetation, and the presence of special status plants within our 6 sites. In addition, we've done some habitat surveys. The RCDs mapped out fish habitat at each site, including pools and cover and things like that. We've been monitoring stream temperature and dissolved oxygen. Dissolved oxygen at one location per site, and stream temperature at up to 3 per site. The RCD has conducted some wet-dry mapping, looking at flow connectivity over a 1-mile reach around these sites. So that's been really useful data to understand how what we're seeing at the wells that are usually at the center of the site translates up and downstream. And LSCE's been installed along with Napa County, has installed a bunch of shallow groundwater wells and measuring stage, which is stage instead of stream flow. And these shallow groundwater wells are dual completion wells, which means that they have a shallower well and a deeper well, so you can understand something about the groundwater gradient, which is very useful for us to know which direction water's going in. I'm not going to talk too much about the monitoring results, but I want to get a couple of things across. One is that we've seen steelhead young of the year, which is what I'll talk a little bit why that's important once we get to the steelhead section. At Calistoga, at the northern end of the reach, a few at the Napa River at St. Helena in 2024, and in Sulphur Creek we saw fewer than 10 juvenile steelhead in 2024 and more than 200 in 2025. The steelhead populations aren't the only one that fluctuate. In 2024, I said earlier, in 2024 we didn't see any Chinook salmon in our snorkel surveys, or the RCD snorkel surveys, and we saw over 200 in Sulphur Creek. In Sulphur Creek in 2025, and more than 2,500 Chinook salmon juveniles in Calistoga at the northern end of the reach. So fish are mostly happening in the upper ends of the watershed. Foothill yellow-legged frogs our observations have mostly been on tributaries. A lot of frogs we observed frogs in Sulphur Creek, including documenting them going from eggs to adults within the season. At the end, so we see them at tributaries and the tributary junctions in the main stem where the habitat tends to be better, and there's more variable flow depths. We also were very surprised last year to get a positive eDNA result at the Oak Knoll site, which is down here at that's our southernmost site. The biologists were out looking at it and were shocked they were shocked to get that result because the habitat looks so poor through that reach for frogs. And it turned out that those frogs, we went back and did some visual encounter surveys and found that those frogs were actually on the tributary Dry Creek that was entering just upstream of where we were doing. This slide sort of tries to summarize some of the habitat conditions where, in general, blue is good. For temperature is the little, or indicating temperature is the little thermometer here. DO indicates the dissolved oxygen. And this thing that looks like a little snake is supposed to represent a flowing river. Yellow is stressful temperature DO or also transition to isolated pools. And red is potentially lethal temperatures in dissolved oxygen or dry, or the channel going to dry. And you can see that we see a variety of conditions. In Bale Slough, um, the channel went dry in our 2025 survey. Here, the dissolved oxygen wasn't good. The temperature was too high. These temperatures in dissolved oxygens are focused on steelhead. And Sulphur Creek, we saw goes dry, but it has slightly better temperatures, but also poor DO by the end of the season. And you can see in most cases the dissolved oxygen levels get bad as the channel flows drop, and as you go to isolated pools. But they can even be bad at the Yountville site, which was the one site that flowed year round. And we found that the dissolved oxygen there wasn't very good either, although the temperatures were okay. And we'll be talking more about individual sites in a second. And in general, habitat conditions were better in 2025 than 2024 for a couple of reasons. There were as I said earlier, there were higher flows in 2025, but also there was cooler temperatures, particularly in June. June, for anyone who tried on the coast to grow tomatoes last year, June was not conducive to those tomatoes getting ripe, and it was relatively cool, which kept the stream temperatures down as well. So based on that monitoring that we've done to date, we came up with some ecological goals, and I want to be clear that these ecological goals aren't set in stone. They'll evolve as we continue to monitor and learn more about the watershed. But there's a couple of goals that are sort of unique to all sites. We want to support groundwater dependent riparian vegetation, which means maintaining summer groundwater within the rooting zone of riparian trees. We haven't seen a lot of evidence that the trees are stressed, but and a lot of the impacts to trees are associated with that incision, which has narrowed the floodplain and means that any sort of shallowly rooted vegetation has to occur down near the bottom of the hill slopes. At all sites, we want to support upstream and downstream fish passage. All of these sites have steelhead and Chinook, and probably Chinook, that are going upstream to better habitat and downstream to go return to the ocean. And we want to maintain ecosystem diversity. But we also have some site-specific goals. We didn't talk about the freshwater shrimp, California freshwater shrimp today, but we want to maintain habitat for them. And we want to maintain steelhead and Chinook rearing where it's present and temperatures are sufficient to not impact them. And where foothill yellow-legged frogs were observed, we want to support them so that there was enough water for them to go from being eggs to little polywogs to, or I guess they're not. I'm supposed to call them tadpoles, to mature frogs that can hop away. So that's where we got to with our goals. And as I said, goals may be adjusted. So next, I'm going to jump ahead in Steph to talk a little bit about flow ecology relationships. Just as a reminder, we need to, this is step 6 within the CEF framework, and it's working its way towards defining ecological flow criteria. But in order to understand the ecological flow criteria, we need to understand how the ecological response for different species to changes in flow. So we first need to assess groundwater flow relationships for base flow. And our focus is going to be on timing, and I'll talk a little bit more about that as we're going on. And we're trying to, we have some preliminary data on this, but we're trying to ask whether summer flow and water temperature are correlated. In general, you would think that as there's more flow, the temperatures might not be impacted as much by solar radiation. But I think we don't really have an answer to that just yet. So hydrology. let's focus on that first. There are two, as I said before, two USGS gauges on the main stem. Those are both co-located with intensive sites. The Napa watershed has this amazing thing, which is called StreamWatch, which is a citizen science assessment of the flow state, whether the channel is flowing, has isolated pools, or is dry, and that gives us a really sort of basin-wide appreciation of how hydrologic condition changes through time in the watershed. We can use the wet-dry mapping to try and understand how watersheds are responding. We've got these dual completion groundwater wells at each intensive site, and the Calistoga well was just installed last year. We're recording stage, and we have surveyed long profiles so that we can correlate stream bed elevation, or wet-dry mapping, and the groundwater depth. These are relatively complex plots. I just wanted to show you what the data looked like, putting it all together. This is we're going to look at St. Helena, which is our second most northernmost site, and then the Yountville Eco Reserve, which is sort of in the middle of our reach, just sort of at the base of where that picture I was showing was taken. I want you to look at two different, or I guess we'll look at three different things on here. The black line is the groundwater elevation as measured at the well. The horizontal green line is the Thalweg elevation closest to the well. That's the bottom of the river channel. So you would think that when you go below that, your channel starts to dry out or at least become isolated pools. And the color indicates the StreamWatch state, where green is flowing, blue is isolated pool, and red is dry. So you can see it if we start with the upstream site. You can see that the groundwater level goes below the Thalweg every year. So this is the St. Helena site, so that's indicating that that channel is at going dry, and it goes dry nearly every year. The groundwater level can bounce back relatively quickly. You often see these abrupt transitions where the groundwater level comes back above the Thalweg relatively fast. It's sort of typical of this watershed and what we see in the groundwater data. And in contrast, as we go down to the Yountville site, you see that the river level is above, or the groundwater level is above the riverbed for most years. And most of the time the channel is flowing. We had 2 years during droughts when the groundwater level dropped below the riverbed, and in both cases the channel went to isolated pools based on the StreamWatch data rather than completely dry. And the StreamWatch data collection is going to be continuing, and we'll be learning. We'll continue to see if these levels correlate to these different flow conditions through time. One of the other the tools that we have is the Napa Valley integrated hydrologic model, which is LSCE has developed, and we can use that in that model. They can turn pumping on and off, and so that model suggests that at St. Helena, the groundwater pumping reduces the flow by 2 to 5 CFS and about 5 to 9 CFS downstream at Yountville. So despite greater impacts at Yountville, because the drainage area is bigger, the hydrology of the basin is a little different there. You don't see the channel drying up like you do at St. So our hydrologic approach, we're going to use for the natural flows database for fall peaks, winter base flow, and spring recession. We can use the Napa Valley integrated hydrologic model for our summer base flow magnitude. That model has a monthly time step, and so it's not ideal for getting duration, but it's really useful for summer base flow. And for the duration of the spring recession flow, we can use both the USGS data and natural flows database, particularly where you're upstream of that large dam. So I'm just gonna show some data from from for a couple different hydrologic characteristics. The start of the dry season, which is also the end of the spring runoff. Um, and you can see that the dry season starts, on average, it starts using the natural flows database, late May most years, with a range from mid-June, or a range from late July during wet year, or early July during wet years, and mid-April during uh, drier years. And that data sort of agrees. There's some overlap with what we see at the USGS data, USGS gauge. On the timing, the USGS gauge at St. Helena suggests it's maybe a little earlier, but it's maybe not a statistically robust result. And these two, the Sulphur Creek, and this is a line from north to south, going from left to right. The tributaries are in the middle there. We can also look at dry season base flow magnitude. Here we've got four different things where it's available. We've got the in blue is the natural flows database, estimated natural flow. That's an unimpaired estimate for those who aren't familiar with that. The integrated hydrologic model with no pumping scenario, or with pumping, is in gold. The green is that model with pumping. Or no, green is no pumping. Gold is pumping. Excuse me. And then orange shows for the two spots with USGS gauges, shows the observed flow. And you can see that the dry season base flow magnitudes for the no pumping scenario and the natural flows database can vary a little bit, but they're generally within a couple of CFS. And just to be clear, this is uh, a log plot with a fake zero here at the bottom. Breaking the rules of log plots, but because flows go to zero, it's very useful for us. And you can see that flows naturally, the natural flows database does not. It has flows going less than 1 CFS, which are probably within the margin of error for whether or not that represents zero flow. So you can see that the flow ranges from site to site. It increases slightly in the summer as you go downstream, but the summer base flow magnitude, we're not talking about 20 or 30 CFS. We're more talking about less than 10 to 15 CFS. These larger peaks that show up down at these sites, down at the south end of the watershed, I think correspond to just picking a weird transition where you're incorporating some of the spring runoff into the summer base flow. Again, those are tributaries in the middle. And then for the spring start, looking at the observed flow and the natural flows database, generally on average starts in right around late March, early April, and can go earlier or later depending on the water year type, with not much, almost no difference observed between the natural flow and at least the mean value of the natural flow and the USGS gauges. So that's the hydrology we're going to use, and I'm going to quickly go through steelhead. So just to show how we're thinking about this, this graph shows the steelhead life cycle. Just to remind us that steelhead start out in the ocean, they migrate into rivers where they hold and spawn, and then eggs incubate. You get juvenile rearing and smolt out migration where they go back to the ocean. But for steelhead, for Chinook salmon, that happens within the season. For steelhead, they stay in the watershed for usually about a year, but sometimes longer. And so it's a really critical part for steelhead is this juvenile rearing stage, which happens year round. And this hydrograph we see at the top shows this is a typical flow. I think I was supposed to replace this with an actual discharge, actual plot from our watershed, which will hopefully be on the next slide. Um, Shows that the summer flows are low when juvenile rearing is happening. So our focus is going to be on summer base flows when the flows are the most stressful for fish, and groundwater use is also the highest and is most likely to affect the magnitude and timing and duration of summer base flows. Um, and as Katie's pointing out here, over submarine survival is a key bottleneck in salamandrid recovery in California. If we look at the spatial occurrence of steelhead, we see that steelhead are where they're the parts of the watershed that they're using varies from year to year. That there's in general water type influences where fish can go and what they can access, and so the rearing locations may change from year to year. In many places, steelhead will use main stem rivers during drier years when access to these higher elevation sites is more limited. And there's a lot of non-flow factors uh, that are important here. The biggest one being the widespread drainage or the widespread incision, which is which has both reduced the regional groundwater level and reduced the available habitat. There's less shading and cover in the stream, less woody debris, increased stream temperature, and reduced habitat complexity. And we have to consider that as we're moving forward. And there's a lot of parts of the watershed that have tile drains in them, and also the tributaries have been reconnected to the main stem prior to pre-European settlement in the watershed. And the reconnection of tributaries and the tile drains are all working to, I think Dave and Nick showed a slide of this. They're all working to get water off the watershed, off the hill slopes more quickly, which reduces the amount of water available for summer base flow. Okay, so that was just a little bit about steelhead. We're still working to develop those flow ecology relationships. One of the things we were thinking a lot about is that the steelhead are probably an important factor for them is being able to get to somewhere with better habitat before the channel goes dry or to isolated pools and the temperature and dissolved oxygen conditions get unsustainable. Now moving on to foothill yellow-legged frogs. Here we actually have the right hydrograph shown above the plot. Good job, Christian. And I've got to say, I've been really enjoying working with foothill yellow-legged frogs. I didn't know very much about them going into this project, and it's been one of my favorite parts about it is thinking about these crazy things that can be in the water and then hop away. But what I want to get across with this plot is that they can't foothill yellow-legged frogs put their eggs in the water. They'll deposit eggs once the flow condition gets suitable. They don't want to deposit them and have them just blown out. So they wait for the spring, and then the egg incubation period, the time it takes for tadpoles to rear and metamorphose, and the time to become an adult are all very strongly temperature dependent. In that happens faster when temperatures are warmer. So the warm temperatures that are bad for steelhead can be good for the frogs. And in Sulphur Creek, where we've been looking, we've seen evidence that there is, even though that channel goes dry in June and July, or in early July in most cases, there is sufficient time for frogs to go through this whole cycle, which has been really interesting, because our question coming into this site was, how are frogs functioning in this place we think we go dry? There's also we've been doing some thinking about what's important for the frogs. So we saw them in 2 of the 3 tributaries we surveyed. We didn't see them in Bale Slough, and the only main stem frogs we saw were at the junction of Sulphur Creek. And one of the things that we've been thinking about might be important is that the tributaries that go dry may actually be beneficial for foothill yellow-legged frogs, because it suppresses bullfrogs who need to rear as tadpoles for over a year, and so that drying and that the tributaries which go dry every year might be beneficial in that case. So next steps, we want to quantify groundwater flow relationships and flow habitat relationships for steelhead and frogs, and we're working on that now. We're going to continue monitoring to better understand population dynamics, particularly in different water year types. Fish will be monitored every year, frogs at least every 5 years, plus when there's very wet conditions or very dry conditions to try and understand those dynamics. We're going to be exploring whether juvenile steelhead can grow sufficiently to migrate upstream or downstream prior to declining levels that prevent migration, which includes exploring the role of proximity to better habitat for steelhead. Where we observed steelhead at Sulphur Creek and Calistoga, better habitat was relatively close. And foothill yellow, we'll continue to look at foothill yellow-legged frogs and their sensitivity to pumping. So just a last summary, and then I'll release you. The stream incision has highly altered the main stem Napa River and its tributaries, and the habitat is generally poor, particularly on the main stem. This is a framework that we need to keep in mind at all times. That's not to say that other things aren't influencing the habitat here, but that incision is a legacy we have to contend with. Most of the habitat for frogs and steelhead is upstream of the groundwater basin, but streams in the groundwater basin are used for multiple life stags of steelhead and frogs. Water quality conditions likely inhibit steelhead growth, but may change based on summer temperatures. So that in cooler summers, maybe the steelhead can be more successful. Linkages between groundwater, stream flow, and stream temperature are uncertain. At lower summer base flows, stream temperature and groundwater at lower base flows, groundwater flux may not be sufficient to maintain cool temperatures. And we're continuing to assess flow habitat relationships. And that is the end of my presentation. Thanks very much.
Thank you, Christian. Does anyone have any questions for Christian? There's one in the chat. Oh, okay. Let's start with the live questions. Let's do David, go ahead. And then Norman.
Hey, Christian. Thanks. That
Hey,
was cool.
Dave.
Daniela says hi.
Oh,
I was just wondering if you all are thinking about taking any measurements of like conductivities and thicknesses and stuff in the hyporheic zone for thinking about some of the process controls on the wetted extent and sort of how much water can the hyporheic zone convey is like for me a big, cool, open question, and I've not really seen anybody taking much in the way of measurements, but it seems like you guys are maybe positioned to do that. Whether or not you had the time or money is a different question, but
we haven't thought about doing that yet. A lot of our reaches have some gravel in them, but they don't have like the thick gravel deposits that you might want.
yeah,
For hyporheic flow, like there are a couple of sites where there's sort of exposed gunky clays in the bottom of the bed, and that's sort of what limited the incision.
yeah,
But that could certainly be important, especially if we're trying to understand in places where the dynamics of the wet dry mapping doesn't make much sense, and
yeah.
trying to think of that connectivity and water quality conditions.
Cool.
Go ahead, Norman. Norman, did you have a question?
Sorry.
That's
The
good.
little audio mute button got me. Thanks for
Been
the
there.
presentation, Christian. Is there any, could we look at one of your slides? I have a question
Sure.
based on a slide. It's the one where you put up dry season base flow results.
Hold on a second. This one?
That one, yeah. Um, I don't want to be too critical here, but I guess I want to ask if you have an idea of why there's a couple cases here that perplex me, I guess is the word I'm looking for, where, if I'm understanding, you've got a scenario where you've got the Napa Valley integrated hydraulic model, and you've got a no pumping scenario, which to me is kind of getting more back to like natural flows. In other words,
Yeah, yeah.
why are they so much higher than what's coming out of the natural flows database itself?
I mean,
Um,
I mean, if you look at that, like, so I'm just looking at the St. Helena one, which is always where my eyes are drawn. I mean, that's a difference of a couple CFS, which
yeah,
is much closer than I thought it would be. There's been um, I think it was a paper by Sarah Yarnell, who's on this call. Um, the net, I think the natural flows database sort of struggles once you get to alluvial groundwater areas, especially for where you have changes where, that groundwater can go up and down, and that can help to control uh, what the base flows are.
yeah,
And
yeah,
so, it's really hard to, when you're doing a sort of statewide, I mean, I guess it's a region-wide model because they break it up into regions. When you're doing a region-wide model, it's hard to account for things like that. And I think that's where that difference comes out of. It's interesting. My first reaction on seeing those data was like, gosh, that's really close. It was I thought that was a I had been concerned that the natural flows database would overpredict the base flows relative to what the modeling was doing, just based on that, or I maybe overpredict or underpredict, but I was mostly concerned that the it just wasn't going to capture those sort of dynamics of being tied to groundwater, and it did sort of. I mean, it looks worse than it is because of the log plot, but I think it did better than I expected.
I mean, you did mention earlier that the reservoir, one reservoir drains, could be influencing the flows at Yountville, maybe. Like,
It can
even,
influence flows at Yountville and Oak Knoll, yeah.
okay,
But I think that tributary, many reservoir is on Creek, and that tributary probably went dry, um, like all the tributaries because they're perched up high on alluvial fans, and so I'm not sure, at least from summer base flow, um, I'm not sure how much that the tributary is um, contributing to summer base flow. There are releases, so we're trying to find out more about the releases in the summer now from that tributary, from the dam, and there I know, are my understanding is that they do release flows at sometimes the year for downstream water rights holder, but we don't have a great handle yet on when that is
right.
and whether there's an effect.
Well, as the previous presenters pointed out, we're trying to estimate something that's immeasurable. So no model's going to do it perfectly,
No,
but
right. I mean,
got to
the
take a
real
stab.
power. Sorry, go ahead.
Well, no, I'm finished.
I was just going to say the real power of models, which, um, in the way I think about them as a non-modeler, so take that with a grain of salt. But I think the real power is comparing different scenarios, right? Like the model is going to there's going to be some uncertainty in the model based on both, because you're trying to replicate all these complex, sometimes fine scale interactions in sort of in a larger scale model. But when you can compare two different scenarios with modeling, it's much more robust, I think. So the pumping on, pumping off change uh, is feels like it's a really that's what models are really good at, and um, but there's got to be some things that we're just not capturing. We're trying to limit those, but it's a work in progress, as
All
are
right.
all
Well, we
things.
have, oh, sorry, I was saying we have we're at noon. So, Christian, thank you so much for your presentation. If anyone has any questions for Christian, go ahead and put them in the chat and he can monitor that for a little bit and see if we can get some answers. So I'm going to skip the roundtable updates today since we are out of time. Our next meeting is on May 12th. And if anyone has any ideas for topics, we can take a minute to like shout them out right now or go ahead and email Chris, or myself, so we can build our agenda for May 12th. Just as a reminder, the presentation slides today and the meeting itself is being recorded and will be available on the Environmental Flows Workgroup website. Um, yeah, and thanks everyone for coming and thanks for our presenters. Like we had really great questions, really great presentations. It's nice to see like Napa putting this all together and integrating the species dynamics into it. So, well, yeah, so thank you so much. And we look forward to seeing you guys in May.
Thank you.
Thanks.
Thank you.
Thanks for some great presentations and information.